Well, 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 look at that, kids. We got a couple triangles for you to look at here. Okay, so today we're going to take a little bit of time and just talk about something that's very special. Special triangles. So what we're going to do with these special triangles is we are going to learn how to do some trigonometry for some pretty common angles without touching a calculator. So this is pretty handy. So the way special triangles work is very simple. You have two different types of triangles that are considered special. You have a nice right angle triangle where the two angles are the same, so they're both 45. And you have a different kind of special triangle, which is an equilateral triangle where you've got 60, 60, and 60. So using some basic facts about Pythagoras, we can figure out what the side lengths of these are, and we can use those side lengths to figure out some trig ratios that's going to allow us to get away from the calculator. So the way a special triangle works in both of these cases here, you take the shortest side possible and you give it a length of 1. So because this one has two equal angles, these two sides are the same. So this is a nice isosceles triangle. Doing Pythagoras, you go 1 squared plus 1 squared and then you square root that. This side here is a length of root 2, and it's that simple. Okay, there's your three sides of a 45-degree triangle. Going over to this one here, we're not so interested in having three 60-degree angles. So what we're going to do is we're going to actually just divide this straight up and down with a right angle division here, or a bisector. So this is no longer 60. That actually turns this into 30 degrees. And on the other side, we have another 30. But I don't even care about this side. This is not relevant anymore. What I care about is this side over here, making a triangle. Okay, so this is a right angle triangle, and again, we're going to call the shortest side of this 1. Now, because this was an equilateral triangle, that means that all three sides are the same, and I cut this side here. This one was cut in half, so this was 1 and this was 1, which means that this side here is 2. Okay, so what we've done, I'm going to get rid of the arrows just to clean it all up. This here is just me labeling the short side 1. That means the longer side has to be 2, the hypotenuse. And this side right in here, if you do some Pythagoras again, you're going to go, let's see, so let's just call that x for now. So it'd be 1 squared plus x squared equals 2 squared. Well, in this case, that would be x squared equals 2 squared minus 1 squared. So that's 4 minus 1, so that's 3. So x squared equals 3. That means x is equal to the square root of 3. So what I formed here is the second special triangle, which has side lengths 1, root 3, and 2. So what we can do now is we can figure out what the trig ratios are for 45 degrees, 30 degrees, or 60 degrees. So I've made a little table down here in preparation. We'll also do 0 and 90. They're kind of like special triangles in a way. So the first one I'm going to look at is the 45, 45, 45 special triangle. So you'll notice that sine from 45 degrees, doesn't matter which one we're talking about, but let's just talk here, opposite over hypotenuse is going to give us a sine ratio of 1 over root 2. I'm going to move that over because I actually plan on writing one more thing here. Okay, so that's 1 over root 2. And I could also work out the cosine ratio from 45 degrees, but I'll use this side because that's the adjacent in the hypotenuse. And it turns out cosine of 45 is also 1 over root 2 with the same value, which brings us to an interesting point. Sine of 45 equals cosine of 45, which is a cool little identity, but more on that later. Okay, and then tan. Tan of 45 is opposite over adjacent. So here's opposite, and here's adjacent. So that's actually 1 over 1. Well, I'm just going to simplify that right away. So that's 1. I'll have some room over here because I'd like to rationalize these. This can be root 2 over 2. I'm not a huge fan of rationalizing them, but it's going to show an interesting pattern, so I'm going to do it. Okay, now let's go over here. We just figured out all the 45s and sine, tan, cos, but let's go to the 30 and 60, 90 triangle. Okay, so what I have here is if I want to go sine of 30 degrees, I'm going to look over here, and the opposite side is all the way down here, so it's 1. And then the hypotenuse is 2, so For a 30-degree angle, the sine ratio is 1/2. And for a 60-degree angle, so looking from the point of view of 60, then √3 is the opposite side to 60, and the hypotenuse is still 2. So I'm going to write this as √3/2. And then we can do the same thing for cosine. We'll go through this a little bit faster because I'm hoping you just get the idea. So 30 will go adjacent over hypotenuse. So 30, the adjacent side is √3/2. So I'm going to write this as √3/2. And I'm being kind of specific about where I put this stuff in the table, just so people know. There's a plan here. Okay, so for 60, cosine of 60, adjacent is the 1 and over 2. So this is 1/2. Which I'm going to actually put here for now. And then tan, we can do the same thing. So tan from 30 degrees is opposite over adjacent, so that's 1/√3. So tan do 1/√3. I'm not too worried about exactly where I put this. And then for 60 degrees, tan is √3/1. Okay. Now what I'd like to do is I'd like to work out the zeros and the 90s because it's going to show a little bit more of an interesting thing here. So if I want sine of 0 degrees, this is where I've got to do that thing where I got to think about this in terms of the Cartesian coordinate system. Okay, so 0 degrees means the terminal arm is just lying flat on the x-axis. So that means my opposite has a height of 0 and my adjacent is exactly as long as my hypotenuse is, because the adjacent runs this way and so does the hypotenuse. So my opposite is 0 and my adjacent and hypotenuse are the same. So sine, which is opposite over hypotenuse, will be 0 over anything, but that's 0. And then cosine will be adjacent over hypotenuse, and if the two are the same, that will be 1. And tan is opposite over adjacent, which is 0, divided by anything, which is 0. Then we can also go to 90 degrees. Let's see if OneNote's going to give me a little more space here. There we go. So the 90-degree situation, again, will look like this. There we go. And we will have 90 degrees here, which means my opposite side is exact as long as my hypotenuse, and my adjacent side is equal to 0. So in that case, sine, which is opposite over hypotenuse, the two over each other will be 1/1. And the cosine, which is adjacent over hypotenuse, will be 0 over anything, which is 0. And then finally, we have tan, which is opposite over adjacent. So anything divided by 0 in math is undefined. Okay, so I've kind of, I've filled in all the parts of my table here, and I just want to fill it in a little bit more. So I actually very specifically wrote things the way I did because of my master plan. And now you will get to see the master plan. Okay, so 1/2 here, these are all the values, but 1/2 can be expressed as √1/2. Don't worry about why I'm doing that. It might be obvious pretty soon, but you'll see. √2/2, √3/2, and you know what I'm going to do? I'm actually going to move this over a bunch because I just want to do one thing here. I could even express 1 as 2/2, or if I really want to follow the pattern, √4/2. That's actually the same thing as 1. So the reason why I'm doing this here, I'm going to do this. This is weird. You would never do it this way, but I just really wanted to illustrate that there's a very, very interesting little pattern here. Sine of 0 is √0/2, and it goes, sine of 30 is √1/2, sine of 45 is √2/2, then √3/2, and √4/2. The square roots go in order from 0, 30, 45, 60, and 90. Isn't that neat? Similar thing here, cosine does this, but guess what? It does it in reverse order. This is 0, which is equal to √0/2. So we can even see, maybe let's pick a different color. Cosine does the same thing, but in reverse order, which is pretty neat. So sine and cosine actually have this sort of flipped relationship with each other here. Tan does something sort of interesting as well. It goes from 0 to 1 over root 3 to 1 to root 3 over 1 to undefined. So that's not quite the same sort of pattern, but it's sort of a little bit of a thing. Okay, so what the point of all this is here, and you don't even really have to use this all. I mean, to be honest, I'm not actually going to use root 4 over 2 when I ask for sine of 90, but it's a cool pattern. Helps you remember as well. But what this is all for is now, if we know these values, and these are values you should memorize, and again, even just little sketchy things here. Okay, come on, OneNote, give me some room, give me some room, give me some room. There we go. Okay. So what you should do is you should be able to quickly draw this, right angle, 45, 45. Sometimes the writing in OneNote just drives me nuts. 45, 45. Okay, and that's bothering me now too. It's hard to do things when you've got OCD. Okay, so then you've got 1, 1, root 2, and then of course this is called the 45, 45, 90 triangle, and you should also be able to easily draw the 30, 60, 90 triangle, and that's going to look something like this. Okay, so there's 30, OCD. This one's 60, and obviously that one's 90. And then the short side is always 1. The shortest side is always 1. The shortest side is always 1, and remember that. Guess what? You'd be surprised how many people wind up doing this. Don't do that. They think 1, 2, 3. That's not the way it works. It actually goes 1, root 3, and then 2. Remember, 2 is bigger than root 3. Okay, so you must memorize those. You must have those in your brain so that when someone says, tell me what sine of 45 degrees is, you don't pick up your calculator and type it in. What you do is you say, okay, well, sine of 45 degrees, here it is. Here's my opposite. Here's my adjacent. It's 1 over root 2. And that's what the expectation is from here on out, that when you see a special angle like 0, 30, 60, 45, 90, you are able to give me the exact value. So here's your little pop quiz. Try this out right now. Pause the video. What is tan of 30? Don't look at the table. Try and work it out. Cos of 45. Sine of 60. Tan of 60. Okay, give it a shot. Shouldn't take too long if you understand. Okay, so tan of 30, what we would be doing is we'd be going up to our special triangle, the 30-degree angle here. We are going to find opposite over adjacent. So the opposite side is 1, the adjacent is root 3, ta-da. Cosine of 45, we're going to go adjacent over hypotenuse, so we're going to say adjacent, which is the 1 over here, and the root 2, that's 1 over root 2. Sine of 60, which is over here. The opposite side is root 3 over the hypotenuse, which is root 2. And then finally tan of 60, which is here, will be opposite over adjacent. I'm not going to write root 3 over 1. And to be perfectly frank, I don't like when you rationalize the denominators. I did that in the table above to show the pattern, but I would just leave cos 45 as 1 over root 2. Okay, so finally, just if you want to make sure that you are getting everything you want, let's actually just take a sec here. Let's just go to calculator. And if we type in, let's say, cos, oh, okay, so, all right, the Windows calculator, just the worst thing in the world. Let's just clear. Get rid of that, get rid of that. Why are you so awful? Get rid of, okay, I don't know. Okay, let's type in 45, and let's type in, I guess we've got to click it like this. Oh, that's just terrible. Okay, anyway, so 45, cosine of 45 is 0.707. Now, we said 1 over root 2, but is that the same thing? And it turns out it absolutely is, because if you go 1 divided by the square root of 2, I think in this calculator you have to push 2 and then the square root button, which I don't even see where it is. Oh, this calculator is the worst. I'm gonna cheat. I'm gonna see if I can do this properly. Okay, so 2 to the power of, let me see here, 2 to the power of this is just the, where's 0.5? Okay, there we go. All right, that was way harder than it had to be. This is such a terrible calculator. Anyway, 1 divided by 2 to the power of 0.5 is 1 divided by root 2. Well, that's 0.707. So there we go. It does the same thing. Anyway, I think maybe my horrible demonstration using the calculator has proven why it's actually more beneficial to go ahead and use special angles. Okay, that's it. Thanks for watching.